Hello. Thank you for attending our presentation on our project, Matchmaker AI, a machine learning approach to enhancing SawYouAtSinai's matchmaking process. SawYouAtSinai was established in 2003 as one of the first Jewish dating platforms, with its mission to help Jews find their soulmates. Since its inception, its matchmakers have made nearly 2,500 engagements. SawYouAtSinai has an extensive user base, with tens of thousands of users. Not only that, but its use is also widespread. People of all ages, locations, and religious observance have found success with the platform. SawYouAtSinai also hosts other platforms, such as YouConnects, JMatchmaking, and Adopt a Shadchan. SawYouAtSinai, as well as all the platforms they host, are exclusively matchmaker-based. This means that all matches are made by matchmakers only. There's no scrolling or swiping. Matchmakers broadly face two challenges. The first of them is knowing who to recommend. With thousands of people in SawYouAtSinai's database, for a matchmaker to go through profiles one by one to find the right match would be equivalent to finding a needle in a haystack. The second challenge they face is knowing the quality of a recommendation. Few matches perfectly align with the preferences of both parties, but many imperfect matches are still good matches. For instance, if a girl says she wants a guy who is at least 6 feet tall, if the guy is 5'10", his height will probably not be a deal breaker. However, sometimes it is less clear. What if the guy were 5'7"? Maybe that would be a deal breaker for her, maybe not. In unclear situations like these, a matchmaker doesn't know if a recipient will accept it or turn it away, wondering why the matchmaker made such a recommendation in the first place. On average, about 1/2 of all matches are labeled on target by the recipient. This means that of the recommendations that are declined by the recipient, about 1/2 of them are still considered to be in the ballpark of what they are looking for. This is significant, as improving the rate at which matchmakers are on target could lead to greater user satisfaction and sustained engagement with the platform. Now, before we get started, we must first discuss the confidentiality of this data. When SawYouAtSinai agreed to let us use their data for this project, we agreed to keep their information confidential. This is important for two reasons. Firstly, it is their proprietary data. Secondly, this is the private information of its users, who never agreed to let their information be shared with the whole world. Some of the practical ramifications of this include the following. We will not be posting this data to GitHub, nor during this presentation will we be sharing any explicit data. All data provided during this presentation will be encrypted or generalized to maintain confidentiality. It is also important to note that we didn't receive all of SawYouAtSinai's data. Some information that would easily identify individuals, such as their names or photos, weren't provided to us. Now, let's get into the data we received. SawYouAtSinai gave us two CSVs. The first one contained information about their members. This included their gender, age, physical details such as their height, body type, hair color, eye color, their place of residence, so that would include country, state, city, their religiosity, both in terms of their level of observance, such as keeping kosher, but also in terms of the community they associate with, such as traditional or modern Orthodox. It also included information about their lifestyle and personality, such as their activity level and hobbies. It also included preferences, their preferences in a match, such as a preference for a height or a certain religious observance. Lastly, it also included information about potential deal breakers, such as if the other person in a match doesn't want to have children, or if that person has children from a previous relationship. The second CSV we received contained information about recommended matches between a man and a woman made by a matchmaker from the members table. So it included the man's ID, the woman's ID, the responses from the man and woman, meaning whether or not they approved or declined the match recommendation, as well as the progress reports from the man, woman, and matchmaker. The information in this column represents how far the match went. That the match could have ended with one of the parties declining, or it could have ended anywhere along the dating process, from just a phone call, one date, many dates, or even engagement. That's what these progress reports are for. Lastly, it also included the match quality and decline reason. These two fields are filled out if one of the parties declined the recommendation. In such a case, they would say whether or not the recommendation was on target, and they could also leave some text as to why they're choosing to not accept the match. Now, let's discuss how we leverage machine learning techniques toward advancing SawYouAtSinai's mission. Firstly, we can recommend matches. With the match data, we created a recommendation engine that can provide new, high-quality matches based on one's previous successful matches. Secondly, we can predict potential matches. Utilizing the member data, we made models that can predict whether or not a potential match will be successful. Lastly, we can analyze matches. Utilizing tools like SHAP-based analysis, we can analyze matches and inform matchmakers if critical criteria will affect a match positively, negatively, or not at all. Now we'll discuss some of the challenges we faced when developing these models.
One challenge that we had is how to define success in matchmaking. There's many metrics we could look at for defining success, like got engaged or not, went out, reached a phone call, or if the match is on target, meaning the match was close, but not for them. But we mainly focused on the on-target rate and the proportion of matches where both the man and woman approve, since raising these measures of success can indirectly improve the others. We also considered using getting engaged as a metric, but that data was mainly withheld, making it artificially low. The data also has class imbalances. So when evaluating models based on these definitions of success, we used metrics like accuracy, precision, and sensitivity to analyze trade-offs and reach an optimized model. Another challenge was dealing with free-form text fields. In order to make use of these fields, we have to convert them into something a computer could understand. We accomplished this through embeddings. So what are embeddings? The goal of embeddings is to convert text into a vector, which is really just a sequence of numbers that captures its meaning and how it relates to other pieces of text. For example, in a two-dimensional space, the word man could be the vector 1, 3, showing how its meaning relates to the words king, queen, and woman. This is a simplified example since real embeddings usually have significantly more dimensions. Now that we know what embeddings are, we need a way to create them. For our project, we used Qwen3, which is an open-sourced neural network-based model that transforms each piece of text into an embedding with 1,024 dimensions. This is possible because Qwen was trained on a large amount of text. The last part of working with embeddings is integrating them into a model. One way to achieve this is by making each dimension of a text embedding a continuous column. But integrating all of the dimensions risks adding too much complexity. So instead, we're able to just use a prefix of the embedding because Qwen3 was trained to make matryoshka, or Russian nesting doll embeddings. This embedding technique is like a Russian nesting doll, since you can remove the outer layers, or ending dimensions in our case, and retain most of the meaning. Therefore, we could just take the first 50 dimensions and then break them into columns for the model to use.
Now that we've discussed the challenges we overcame before building our models, let's now discuss the models we made. The first thing we did was build an engine to recommend matches. To do this, we use collaborative filtering. Collaborative filtering works by taking users' ratings on different items. It then calculates the latent factors for all the users and items. Latent factors are vectors that represent the preferences of a user and the attributes of an item. For instance, we can see on the right that users 1 and 2 share similar tastes, whereas users 3 and 4 differ. User 5 really likes all the items, whereas user 6 dislikes all of them. We can also see that items 1 through 5 have a wide range of reviews, whereas item 6 has broad appeal. Using the latent factors, we can find which users and items are similar to one another. The way we do this is by using cosine similarity. The cosine similarity function is the cosine of the angle between two vectors. If two vectors are similar, then they also point in the same direction. And if they point in the same direction, then the angle in between them is small. And if the angle in between them is small, then the cosine function will be close to 1, as the cosine of 0 is 1. If the angle is closer to a right angle, then the function will be close to 0. If the angle is close to 180 degrees, then the function will be close to -1. Now that we have a way to measure how similar two users' preferences are to one another, then we can simply recommend to a user the things that a similar user liked. Going back to our previous example, just as we can visibly see the users 1 and 2 have similar preferences, so too a computer will be able to calculate the vectors and use those vectors to recognize their similar preferences and make recommendations based on it. Now, in matchmaking, it is really the same idea. In this context, who is the user and who is the item is all relative. For women, they are the users and the men are the items. And for men, it is the reverse. On the right, we have a table representing the preferences of different women for different men. And on the bottom is that same table showing those men's preferences for the women. Now we will show an API we developed to generate recommendations with someone's ID. Here we input the encrypted ID number and the number of recommendations we would like. The API then gives back brand new match recommendations. Now, on the right, we can see basic summaries about the person we requested recommendations for and the first recommended match. We can see here that at least with this small amount of information, this seems to be a pretty good match idea. They're close in age, their religiosity levels are similar, and they even live near one another. While this model doesn't have the final say on the matter, as it sometimes makes peculiar recommendations, it is certainly a good place for any matchmaker to start from. However, for further analysis on potential matches, we will utilize other techniques.
So next we created models for predicting matches. One type of model we use for predicting matches is neural networks. Neural networks are inspired by how the human brain works. They're made up of layers of simple processing units called neurons that learn patterns from data. The goal is to feed it input and have the model learn from it to produce the right output. It uses the input by comparing it to the prediction to learn the patterns, sort of like using a cheat sheet that gets smarter the more it studies. It is composed by 3 layers as we see in the diagram. It starts with the input layer. This is where we feed the model our data, in our case, the age and the height or the traits. Then the data flows into one or more hidden layers. This is where the learning happens. The network adjusts internal weights and looks for patterns as data passes through. Finally, it reaches the output layer, where we get the model's prediction, like its preferences or if it's a match. So in reality, neural networks can only predict based on what it's fed. For neural networks, we use a library called FastAPI, which makes it easy to import, split, and pre-process data, which is then used to train a deep learning model. Our process was we imported the data into a pandas data frame. We then defined which columns were categorical and which were continuous. Then we split the data into training and testing sets. Then we do things in like categorifying the labels, filling missing values, and normalizing numeric inputs. And finally, we were able to train and evaluate our models. FastAPI allowed us to focus more on analyzing and experimenting since it handles most things under the hood. So before we move on, let's talk about a challenge that we ran into, overfitting. Overfitting happens when a model learns the training data too well, including the noise and small details that don't generalize to new data. For example, let's say there's only one person in the training set whose name starts with the letter S, and that person was a successful match. If the model overfits, it might assume that everyone with a name starting with S will also be a good match, which would be a problem. But the model doesn't know that unless we guide it. On the left, you see a model that generalizes well and finds a clean trend that works across different examples. On the right, the model is too flexible. It's trying to perfectly match every training point and ends up creating a wavy, complicated prediction line. We ran into overfitting a lot for neural networks, so we also started experimenting with other models.
As explained, we found our neural network models relatively unhelpful in achieving our goal of predicting matches, particularly due to overfitting. We therefore switched and attempted tree models. The most basic tree model is a binary decision tree. A binary decision tree can be displayed as a flowchart in which we start on the top and go down based on binary questions on the data. These questions are determined based on the data set we gave it. On the bottom of the tree, we can see the ratio of positive and negative results based on a particular path. Once a decision tree is created, we can then predict the outcome of other matches by going down the same tree. The problem with these binary decision trees is that they can overfit to very specific data. They are therefore unhelpful when trying to predict results based on data with outliers. For example, in the example tree below, we can see that this tree focuses on whether the female's name starts with an A and whether the male's name ends with a B. This, however, is completely irrelevant and should have no contribution to our prediction. We therefore decided to use a random forest model, which can handle more nuanced data and generally doesn't overfit. The random forest model is a combination of many decision trees, usually around 100. However, each tree has a different subset of data. For example, in our model, we took 80% of the data for each tree. However, each tree contains a different 80% of the data. When predicting a match, our model will go through each tree and take the majority of outputs as the prediction. What the random forest model enabled us to do was to create a model which, similarly to the decision tree, explains why certain prediction occurs and the factors which affected the flow of each decision. However, unlike decision trees, random forests generally don't have a drawback of overfitting. Based on this random forest model, we were able to make an API which can predict the quality of certain potential matches, and it can explain which factors affected the potential match most. What we see on this slide are screenshots of that API. On the left, we see some of the inputs we put into the API. We could put certain features and we could check those off, while others we can input numbers into, such as the height, the age, and the physical distance between the two members in the match. What you can see is that the first match on the top right was unsuccessful, with one of its worst features being the woman's religious identity, with the woman describing herself as just Jewish. However, once we change her religious identity to modern yeshivish, we can see that the match is successful, as shown on the bottom right.
Another way to predict match quality is by using XGBoost. XGBoost works by building out many decision trees where each tree focuses on correcting the error from the previous one using a subset of the data. Repeating this process creates many trees which combine to create a robust model. XGBoost is also resistant to overfitting, mainly due to built-in regularization that discourages overly complex trees, and because gradually adding trees allows the model to learn slowly without making large jumps. A final benefit is that it's fast and efficient to train. Using an XGBoost model trained on most columns and embeddings, we achieved a mutual approval rate of 9.26% compared to the matchmaker approval rate of 6.54% at a 35% confidence threshold. This will be a 40% improvement in the match approval rate, allowing users to spend less time waiting for a good match. The downside is a 6.2% false negative rate, which is the percent of mutually approved matches being misclassified. We also looked at the performance of different confidence levels and observed a trade-off. Looking at the three confusion matrices, as we increase the confidence level needed to categorize a match as mutually approved, the model approval rate increases significantly. However, the false negative rate also goes up significantly, with many good matches being misclassified. For our task of minimizing bad matches, a high false negative rate is not an acceptable trade-off. So we went with a 35% confidence threshold. In addition to predicting if a match will be mutually approved, we used SawYouAtSinai data to predict if a match will be on target, which means at least close to what a person is looking for. Our low threshold model is 9% better at predicting on-target matches than the matchmakers, resulting in a 71% on-target rate with a low false negative rate of 3%. In contrast, our high threshold model is 19% better than the matchmakers, but with a high false negative rate of 14%. Using the low threshold model, we can help the matchmakers make more on-target matches at a low false negative rate. For predicting mutually approved matches, we made an API that takes two encrypted user IDs as shown at the top. Then it gives probabilities plus the most important factors used for its prediction. In this case, the model gave declined more weight at 54%, and this match was indeed declined.
So now let's begin analyzing. We analyze our models using SHAP. SHAP is a machine learning tool that creates a certain weight to each input. It uses concepts from game theory, where each input acts like a player in a team. The goal of the game is the model's final output, the prediction. SHAP tests different combinations of inputs, just like testing different lineups in a game, and then assigns each feature a value showing how much it contributed to the outcome. As we see in the graphs below, a user inputs a player into the game and SHAP spits out how much weight each player has. We can see how the user is inputting things like age and weight, and SHAP outputs its values. Now, to better understand what is happening under the hood, let's run through an example. Let's say we are doing a UN voting scenario where the US has 30 votes, France has 15, and Japan has 10. The goal is to reach 50 votes to pass a resolution. As we see, with the US alone, they only have 30 votes, which is not enough. And even if you have the US and Japan, they have 40, which is still not enough. But then when you combine all three, they get to 55, which means that they're able to pass the resolution. This is showing us how SHAP works under the hood. It tries every possible combination of inputs to figure out which one really makes the difference. In this case, we see that even though France and Japan together give 25 votes, it's only when we add the US that we pass, meaning the US has the biggest impact on the outcome. However, France and Japan are still important because it wouldn't have passed without them. SHAP does the same with features. It figures out which inputs were more critical to reaching the goal, which is the prediction, and gives each input a value on how it affects the outcome. So now let's see how SHAP works with one of our models. This SHAP summary plot tells us which features influence the model's prediction for preference towards an athletic build. From this graph, we can see that individuals with a medium or broad build tend to prefer athletic build less, since their data points are mostly associated with negative SHAP values, meaning those traits pulled the prediction down. On the other hand, people who are introverted tend to be more neutral in preferring an athletic build, since their SHAP values are spread across both positive and negative sides, indicating that being introverted doesn't strongly push the prediction in either direction. To make SHAP visualizations more accessible, we built an API that supports 3 core functions. Let me walk you through each one. For the first part, you simply pass in the model type, whether you want to predict trait preference or religion sector preference, and the gender you're interested in. And it returns all the SHAP graphs for that segment. This allows us to zoom out and see everything that's being affected across a group. For the second part, and you provide the model, gender, and a specific user ID, and it returns a SHAP explanation for that individual. This is great for more specific analysis of a single person. For the third part, you choose the model and gender, and then manually enter custom input values, like personality traits, physical features, and so on. It's a way to experiment by tweaking traits and instantly seeing how the model's reasoning shifts. With all this, we are able to analyze our model as a whole, individually, or with custom inputs.
Now that we have finished discussing the models we developed, we would like to take a step back and show some of the behind the scenes that we thought to share in this presentation, specifically our approach to processing, enriching, and reconciling the data. In order to process our data, we made an ETL, extract, transform, and load pipeline. We were given the data from SawYouAtSinai as a CSV file, which we decided to transform into a SQL database. We started with running a Python script to pre-process both the CSV file and the SQL database, which we transferred it into. To maintain consistency on all our machines, we packaged this whole process into a shared Docker container. Within each of our programs, we use Pandas data frame to analyze and manipulate the data. One example of us enriching the data was the addition of a distance column. Within the members data, we can see the state and city where the member lives. However, we found that distance would be a better way to determine the compatibility of a match. We started with an API to calculate the coordinates of each location. However, we soon ran into a problem with each API call taking over a second, which in turn would take 20 days for us to find the coordinates of each member. We therefore came up with a plan to create a cache database. If the city is found in the cache, we just use those coordinates. Otherwise, we call the API to get new coordinates. We then add that city and its coordinates to the cache. Once we get the location for each member, we can then easily calculate the distance between each member in a match. An example of us reconciling the data was the addition of the overall progress report column. SawYouAtSinai receives progress reports from members about suggested matches. However, we found that progress reports from different parties in a match, such as a male, female, or matchmaker, weren't necessarily in sync. We therefore created another column which contains the most recent progress report.
So now let's wrap things up. First, we should go over the key accomplishments for this project. We started with 2 data sets, members and matches, and we spent time exploring and loading those into a working environment. Then we built tools to support matchmaking using machine learning models. These models can predict the likelihood of a match working out between 2 users, it could show what helps or hurts that likelihood, and even if you just give it one profile, it can suggest preferences or output a list of potential matches. We then analyze the results using tools like SHAP to interpret what the models were learning and where those predictions came from. And finally, we created user interfaces to be able to interact and explore our data. Now that we've wrapped up our project, let's talk about how we can improve. So first, we want to use more data. And like with any machine learning task, the more data you have, the better your models can learn. Next, because of confidentiality requirements, we didn't have access to all the fields or the most up-to-date information. That led to issues like missing values or outdated records, which we'd want to clean. Finally, we like to improve our models. Some ideas would be to combine different types of models like neural networks and tree-based models to boost performance. We could set up automated retraining cycles as new data comes in, and even building feedback loops so that the model can learn from user behavior over time. Here are the technologies we use and learn throughout our process. For data learning, we use CSV files, Docker, Postgres, SQL, and Python. For model building, we use collaborative filtering, FastAI, decision trees, random forests, and XGBoost. And for analyzing and presenting, we use SHAP and FastAPI. And that's it from us. And thank you so much for listening. This was a really intense and rewarding project, and we learned a lot through the process. We truly appreciate your time and attention, and we hope you found it interesting. On behalf of myself and the whole team, I want to express our sincere thank you to Moshe for mentoring us throughout this project. Your guidance and insight gave us a real taste of what it means to work in a professional environment, and we learned so much from you. I'd also like to extend a special thank you to SawYouAtSinai for giving us the opportunity to be a part of your process and for granting us access to such meaningful data. It was incredibly valuable to work on something real and impactful. We're truly grateful.